Hello everyone, my name is Shane Workus, and this is a presentation on my bachelor's thesis for the Turku University of Applied Sciences, titled Environmentally Reactive Sound Design. In the summer of 2021, I was invited to join Boost Turku's Startup Accelerator program, also known as Startup Journey. I developed an idea for a startup called Furniture Music, whose aim is to reimagine the way that sound and music are used in public or common spaces. The topic of my thesis then became the development and deployment of a proof-of-concept device capable of playing music that would develop in response to changes in the surroundings. I used this device while pitching the startup in order to give a clear idea of what I was proposing. In this video, I will explain the device specifications, the implementation of the system, and the impact of the device on Furniture Music's pitches and presentations within the Startup Accelerator. The first specification was that the object should look familiar from the outside in order to give an anchor to the more novel behavior of the computer inside. With this in mind, I chose to repurpose a vintage radio cabinet for the overall enclosure. I pulled out all the existing wiring and did some light modifications to the surface of the radio to prepare it for the hardware that would be installed. For the main processing unit, I chose a Raspberry Pi 4. My focus was on the accessibility and relatively low cost of these microcomputers, along with enough processing power to manipulate audio signals in real time. Additionally, I have become quite familiar with the Raspberry Pi line of microcomputers over my time at TUAS, so I was able to avoid a steep learning curve by going with something I already knew. In order to get the device to react to the space around it, sensors needed to be chosen to communicate these environmental changes. I chose to use a motion sensor and an array of light-dependent resistors to track movement and changes in light. To get this data into the Raspberry Pi, I developed a Pi hat, also known as a hardware-attached top, containing input connections for the sensors, as well as an ADC or analog-to-digital converter chip to convert the values from analog voltage to digital information that a Raspberry Pi can read. Additionally, I used a single Genelec speaker and a Native Instruments USB audio interface to convert the digital signals from the Pi into audible analog signals. With the hardware set up, I chose the audio programming environment Super Collider to process the data and output sound. Super Collider is an open-source programming language and integrated development environment with a synthesis engine based on the server paradigm, familiar to networking applications. This environment was ideal for the project because it allows low-level control over the sound, the ability to send and receive standardized messages with other computer programming languages like Python, and a small footprint, meaning it runs reliably on a Raspberry Pi. The overall architecture shown here reveals that in its skeletal form, this is basically an analog to digital to analog signal flow. The Raspberry Pi receives the sensor data through a Python script and then sends that data to Super Collider. Super Collider then uses that data to change the parameters of the ongoing sound before sending it out to the speakers. Now I'll talk a little bit more about the sound content and the code used for the system. I created audio recordings using Ableton Live, a digital audio workstation, and stored them as samples. These recordings were divided into 3 layers: a bowed guitar drone, a recording of bird sounds, and an array of 10 recordings of short piano gestures, ranging in length from 5 to 15 seconds. In Super Collider, a synth represents a single sound-producing unit. 2 different synth definitions, or Synth Defs, were created to control the playback of the audio recordings. The first Synth Def is simply designed to load the audio file as a buffer and play it back on a single channel at a single amplitude. The other Synth Def is designed to take 2 separate audio files as a buffer and play them back simultaneously in an asynchronous loop. Additionally, and most importantly, the Super Collider method xFade2 has been implemented to allow inversely proportional volume control between the two sound files. This type of sound manipulation is also known as crossfade. The SBC PIR motion sensor is used to trigger a random piano sample from an array of 10 samples. In order to send messages from the motion sensor to Super Collider, a Python script was written to wait for a motion sensor event and then transmit an open sound control message. By listening for an OSC message with a predetermined name, Super Collider is able to receive a new message every time the Python script sends one. Additionally, a 10-second wait time is initiated after a sample is triggered to avoid excessive overlapping or distorting of the signal. Voltage data from the light-dependent resistor arrays are sent to Super Collider in a similar fashion to the motion sensor. However, the information is sent as a floating point number rather than a Boolean value. It is notable that the message is sending the raw analog to digital converted value from the light sensor, not the converted voltage message. The idea here is simply to avoid several unnecessary conversions, as will be seen later. When Super Collider receives these messages, it converts the raw ADC value to a decimal value between -1 and +1 using a linear scale. This decimal value is used to set the crossfade between the bowed guitar sample and the recordings of birds. The overall effect is that when there is more light, the birds are louder and the guitar is quieter, and when there is less light detected, the inverse happens. The birds are quieter and the guitar is louder. Because the light conditions in different spaces vary so widely, the minimum and maximum light values are evaluated and changed on the fly by the operator, a process for which Super Collider is built. The difference in response between when I pitched the business idea of furniture music with the proof of concept and without was stark. Without the device, most of the time was spent explaining how the product would function and trying to get the audience to imagine it. With the ability to demonstrate the product quickly at the outset, I could concentrate on other aspects of the pitch that were more in line with the content of the Startup Accelerator. There were 3 rounds of pitching competitions throughout the accelerator. With the aid of the prototype, Furniture Music was chosen as a finalist twice and offered an additional opportunity to pitch to an additional group of investors. Also, as a result of the pitches, Furniture Music was invited to set up the device in a relax room at the Shift Business Festival in Turku. The room was designed to give respite from the frantic energy of the festival. The overall response from the attendees was positive, even if the effect was a little bit too subtle. One takeaway from the festival was that the ambient light doesn't change enough to register meaningfully in sound. Perhaps using a larger array of light-dependent resistors would allow for the tracking of shadows in a more noticeable effect. Another option might also be to use a video camera to track motion instead. Meaningful information could be taken from the environment through means of a microphone as well. Overall, the development of the prototype aided greatly in the pitching and describing of the type of work Furniture Music is interested in doing. While this is just one iteration, I believe it contains the basic tool set that will continue to be used in the development of these environmentally reactive sound devices. Thank you for watching.